Hello. Today we're doing cryptography 3. It's going to be about symmetric encryption. Oh, wait, down. Am I supposed to point it somewhere?
Why not? Yeah, I mean, it's fair. Sometimes it doesn't work when you're not close enough to the left. Or maybe I just didn't click on it. Gosh. Yeah.
Okay, yeah, there were changes to the infrastructure last Friday. So if any challenges or whatever don't work, then let us know. This is the meeting flag, and this is a picture of how encryption, well, kind of works. Okay, so what is symmetric cryptography? The symmetric cryptography is when we have a key that both sides share, and then we use that to encrypt and decrypt messages. And so the advantage of this over asymmetric cryptography is that it's much faster. And but first, to exchange the key, we usually use asymmetric cryptography like Diffie-Hellman key exchange. And so we prefer to only do asymmetric cryptography once at the beginning, then we continue with symmetric cryptography since it's faster. So the best way to do symmetric cryptography is just use a one-time pad. Basically, this has perfect secrecy, but the disadvantage is that you have to share the key, and the key has to be the same size as the message that you want to share. Basically, so if you want to share it with asymmetric cryptography, then you may as well just do everything with asymmetric cryptography. So it's kind of useless in this case. One way to fix this naively might be to just split the input into blocks, and then you can have a key of fixed size and just XOR each block with the key. And now this leads to a bunch of problems. But the general principle behind this is useful. So we have block ciphers, which mean we can just split the input into different blocks of fixed size, and then we apply some cipher or algorithm to transform it into ciphertext. And this is weak. So this has plenty of weaknesses. For example, this is just the naive method of XORing each block with the key. But for example, now if we have the same character, it will always like the same character in each position in the block. For example, if the block is 8 bytes, then if the first byte is the same in different blocks, we're always going to get the same output. We can also add any two characters in the same block together, or like in different blocks in the same position in that block to get the XOR of those characters, and this gives us a bunch of like correlations between the blocks, and we can exploit that. So to give a description of what makes a good block cipher, the cryptographer Shannon introduced two concepts, that is diffusion and confusion. Confusion is making the ciphertext depend on the key and the plaintext in a way that can't be easily expressed. In particular, we want this to be expressed using a very nonlinear function, because if we had a linear function, we can easily reverse that. And so yeah, the XOR method is bad at that because it's just a linear function and it can be easily reversed. And the second concept is diffusion, and that means each byte in the plaintext should affect as many bytes as possible in the ciphertext. And The point is that, so if we change just one byte in the plain text, we don't want it to be, we don't want it to be easy to tell if two plain texts are close or if they're very different just by looking at the ciphertext. So we want the ciphertext to look completely random, depending on what the plain text is. So the best symmetric cryptography method we have now is AES. And it's a block cipher that operates on 16 blocks of 16 bytes. We have 3 different bit lengths for the keys, either 128 bits or 192 or 256. And so the algorithm works by first, we split the key into a bunch of different round keys, and we represent each block by a 4x4 matrix. Since we have 16 bytes in the block, we can just put the first 4 bytes, then the second 4 bytes, and so on. Next, we perform 4 operations on the matrices. So first, we shift the rows. As you can see in the picture, we have, does this work? Yeah. So in the first row, this is index 0, so we shift each byte 0 positions. We just don't change the first row. And you can see the rows are the same. In the second row, we shift each byte 1 position. And you can see this shifted by 1. And in the second one, we shift each one by 2 positions. So this is 2, 0, this is 2, 2, and so on. And the point of this is that we're providing diffusion in the horizontal direction, because at the end of all of the operations, we're going to XOR it with the keys. So since we do this in every round, the keys, like each byte of the key will be XORed with as many different bytes in the ciphertext as possible. And so the second operation is a bit more complicated. For each column, we multiply it with a specific matrix. And this also provides more diffusion. How it works is a bit more complicated. But the point is that it provides diffusion. So, and now, like if you notice, the first 2 operations we used for shifting rows and matrix multiplication, both of these are linear functions. So the third operation is to provide confusion. We want to make it nonlinear. And the way we do that is by using a substitution box. So basically, this is just a lookup table. We look at each byte, we replace it with a different byte. And the box is specifically designed to be as hard as possible to like describe as a function. We can describe it, but it turns out to be a high degree polynomial, and it's very hard to do anything with it. So then we XOR it with the round key. And now we repeat all of that a bunch of different times until we finally reach the ciphertext. So all of this just works on on each block of the input. So to turn this into a cipher for the whole input, there are a bunch of different modes that we use. And for example, and each of these has advantages and disadvantages. The most obvious way to do this is just, it's called ECB, Electronic Cookbook. And basically we just provide the plain text to the cipher with the same key independently. So this is the simplest way, but it has some disadvantages. For example, if you use the same plain text in multiple blocks, you're always going to get the same output since the cipher is deterministic. So to solve this, we have CBC, which just means that like before entering the second block of plain text into the cipher, we XOR it with the first ciphertext, and so on. So the advantage of this is, like, if you look at if we encrypt this penguin, we see here, if it's ECB, then it still looks like a penguin. And the reason this happens is because, so for example, a group of white pixels will still, when we encrypt them with ECB, they're all going to go to the same colors. So we can still kind of recognize what it looks like. But if we use CBC, then it all looks completely random. So what happens if the S box, so yeah, I made a big deal about it being nonlinear, but what happens if it is a linear map? Then what happens is that, so yeah, since the first two operations are both linear or affine maps, this, in the context here, it just means we're multiplying it by a matrix and then possibly XORing it with the number for, like when we add the round key, we're XORing it. So this is an affine map. And affine maps are easily reversible because we know how to invert matrices, and we can invert XORing just by XORing again. So if every operation in AES is linear, that means the whole thing is linear. So we can reverse all of it. So that's why we need the S box to be nonlinear. If the S box is still nonlinear, but it's still representable with a low degree polynomial, like a quadratic function, then it's also possible to reverse. But like the method is a bit more complicated. So the second way of having a symmetric cipher is to use stream ciphers instead. These all rely on pseudo-random number generators. Essentially, they're just ways to start with a sequence of random numbers or seemingly random numbers and extend them in an unpredictable way where we can't really learn anything about previous bytes. And the advantage here is, so if we start with a key, we can extend it pseudo-randomly to get a key stream. And when we have, so then we can just XOR those with the inputs with the plain text instead to get a ciphertext. And there are a bunch of different ways to do this. Sometimes instead of extending the key, we start with IV, an initial value, and then we use the key as some kind of input to the pseudo-random number generator. So this is an example where we do that exactly. We use the IV and the key to generate a key stream, and then we XOR that with the plain text to get a ciphertext, and we can decrypt it in the same way. So for example, there are plenty of ways to do this. There are a bunch of different modes for AES, like the counter mode and GCM, which turn it into a stream cipher. There's also SIGPwny, which is very popular, and so for older hardware that isn't optimized for AES, it's used a lot in that. We also have RC4, which is used in Kerberos, and it's completely insecure. So you can, it's easy to decrypt if you're using an old system that uses it. And there are others. For example, this is an example of an AES mode that uses a stream cipher. As you can see, we start with an IV, we encrypt it with the key, and then we XOR it with a plain text to get a ciphertext. And then we go on. So yeah, there are also, so here are a bunch of attacks on stream ciphers and also block ciphers. First is bit flips, and this is in the OFB mode of AES. This is also a stream cipher, and you can see up here there's a diagram of how it works. So yeah, we start. Yeah, so essentially what happens is that since we XOR the plain text with something to get the ciphertext, if we just flip a bit in the ciphertext, it will also flip the same bit in the plain text. And so if you want to send a plain text to someone and you want it to decrypt to a specific value, then we can do that. Yeah, just by flipping the same bit in the ciphertext. And the other CFB mode protects against this, since it uses like instead of XORing this the key stream with, instead of like using the same key stream as an input to the next key stream, it instead uses the ciphertext. So if you change the ciphertext, then all the next blocks get scrambled. Now we also have zero logon. This is an attack against Microsoft's NetLogon, and in older systems, it's just lets you log in without any credentials. How it works is essentially the server. So essentially, how it works is how the protocol is supposed to work is that the client provides a challenge and the server also provides a challenge. And so how the server calculates that challenge is that it starts with an IV and it has a message here. And it's supposed to generate this randomly. It also generates the key randomly, or no, it generates the key based on its own challenge and the client challenge. And it's also based on the password. So if you have the password, then you can calculate the key. And since it gives you its challenge, then you can just decrypt. Like you can just calculate what you're so you have this, the server will tell you this, and if you have the key, then you can calculate this, which is the result of performing AES CFB mode encryption on it. And then if you send this to the server, then it will authenticate you. But so what Microsoft did is that they just chose the IV to be all zeros. So the server lets you control this message after the IV. And what happens is that if you send it, so the result, what happens is if the key starts with zero byte, then what will happen is that when it encrypts, when it encrypts this, since you don't know the key, we just assume it's a random. We assume that this is just a random function. And if it starts with 0, then it adds a 0 next to the message. And that's how the encryption works. It just takes the first byte of the output and it appends it to the IV. So now this IV is the same as this IV. So when it inputs it again to AES, you're also going to get a 0. And then it will append that again to the IV, and it will remove the first bit, and it will continue doing that. So in the end, all of the outputs are going to be zeros. And so this has a 1/256 chance of happening, since it happens if and only if the first encryption had a 0 in the beginning, and we're assuming this is a random function. So if you just tell it that the password you're supposed to send is all zeros, and you repeat this 256 times, or at least until the 1/256 chance happens, then you're going to authenticate, and then you can do whatever. Wait, this is broken. But yeah, that's essentially it. Next The next meeting, I believe, is Java reverse engineering. Yeah, and so that's this Thursday. Next Sunday will be point 3, which is raw. And yeah, so thank you for coming.
Yeah,